This video is on Unit 12, Lessons 5 and 6, and Lesson 5 starts with talking about independent events. So you guys should know what the word independent itself means. So when we apply that to probability, basically independent events are when one event does not affect the probability of the second event. So independent, they don't depend on each other. So it's the opposite of depending. So if they were dependent, then the probability of one event will depend on what happened in the other. So for example, if you were pulling marbles out of a bag and you did not put the first marble back, then the probability of drawing a red on your second draw would be different than drawing a red on your first, because there's not the same number of marbles in the bag for your second draw. So if one of the probabilities will depend on one of the, like the first event, then that's dependent. If it's independent, they have no effect on each other. So we are going to do a quick example to see the difference. And here is actually the formal definition. Before I do the example, I should probably explain what this means. Basically, it means, remember this line means given. So if you were to find the probability of event A happening given that event B happened, if that turns out to be the same as just the probability of A happening, so basically the fact that B happened had no effect on A happening, then you can say they are independent. So what you're going to want to do is you're going to want to find, like if I said find the probability that I get a red marble given I got a green marble. Well, if the probability of getting a red itself is the same as finding the probability of a red given I got a green on the first one, then you'd say they're independent if those are exactly the same. If they're not the same, then they are dependent. And vice versa, this is the same thing except B came first. So if the probability of B happening given that A occurred is the same as just the probability of B happening, then they are independent. So you're going to see that right now in this example. One of these, A or B, is independent and one is dependent. So the first part, first of all, we are using this chart. We're examining this chart. It is 57 sixth graders, and they were asked, based off of if they were male or female, what subject was their favorite out of these four. So part A says, does it appear based on the data in this table that the preference for math as a favorite subject has dependence on their gender? So we are going to show the analysis and explain your findings. So the first thing we want to do is find the probability that math is their favorite subject no matter what their gender is. So the probability that a student preferred math is 18. There were 18 kids out of 57 total, which we are going to convert to a decimal so that we can compare it to the other probabilities. It's about 0.32. Now we're going to see if that will change if it's given that we're looking at males and then given that we're looking at females. If it's truly independent, those will all be the same because it shouldn't matter if it's male or female. So let's take a look. We're going to find the probability that the student likes math given, and we'll do males first, given that it was a male. So this means we are only looking at the males. There were 10 kids, 10 boys out of 27 total that liked math. And that is approximately 0.37. So right there, they are not the same. So we know it's dependent, not independent. And we should check the probability that a person likes math, given that they are a girl, they are female. So we're only looking at the females this time. There was only 8 girls who liked math out of 30 girls total. That is approximately, I should use the squiggles, 0.27. So because none of these are the same, okay, none of those are the same, None are equal. So therefore it is dependent. If they were truly independent, then it wouldn't matter if it was male or female, all the probabilities would be the same. So let's check another subject. It says, does it appear based on the data that the preference for social studies as a favorite subject has a dependence on a student's gender? So we're doing social studies this time. So first, let's check what's the probability that any student liked social studies, whether or not they were boys or girls. So social studies, there were 19 out of 57 total, which is approximately 0.33. Now let's see what's the probability that somebody liked social studies given that they were a boy. So we're only looking at the boys this time. Social studies was 9 out of 27, which if you can do that mental math in your head really quickly, that's 1/3, whoops, squiggles, which is approximately 0.33 again. So far it looks like it is independent. And the last one, social studies, given that they are female, so we're only looking at the girls. Social studies was 10 out of 30, which is 1/3 again. So that's 0.33. So this one does appear to be independent since all of the probabilities are the same, whether or not, it did not matter if they were boys or girls. It was the same probability of liking social studies. So that is how you determine if an event is independent or not. We are moving on to lesson 6. Lesson 6 talks about, this title is kind of deceiving because we are going to talk about ors as well. We're not just going to talk about ands. But before we begin, we need to travel back to, I think it was 7th grade when you first talked about different words that mean different operations. Like real quick, for example, sum means add, product means multiply. Well, back when you talked about those words in 7th grade, there were 2 words you should have discussed as well, or versus and. When you hear the word or in mathematics, you should be thinking you are adding. When you hear the word and in mathematics, you should be thinking multiplying. Okay, so you need to think of those 2 operations. You need to associate those 2 with those 2 words, because in probability, you need to recognize that if they want you to find the probability of event A happening or event B, you're going to add those 2 probabilities together. But if they said A and B, you're going to multiply. So it's very important that you know these 2 words, which operation are associated with them. So let's look at our first example. I separated the notes into independent versus dependent, so you can take a look at what you would do. So if the 2 events are independent, which actually that is the first question in exercise 2. We are spinning a spinner twice, and it says, are the outcomes of the 2 spins dependent or independent? They are definitely independent because the first spin doesn't change the probability of the second spin. Whatever you get in the first spin has no change on the probability of what will happen on your second spin. Now, if I said, once you spin the first spin, like that number disappears and you can't get it again, then yes, it would be dependent, but that's not the case. So independent because the first spin doesn't change the probability of whatever they're asking you to get on the second spin. Okay, so hopefully that makes sense to you, the whole dependent versus, why did I write second chance? This is why I can't talk while I write. Second spin. Dependent versus independent. If it depends on, if what you get on the second time depends on what happened on the first time, then that's dependent. But if the first one doesn't affect the second one, then you're independent. So now it says, what is the probability that you will get an even on the first spin, and, does everybody see that word and? A number greater than 5 on the second. So here's what we're trying to find. The probability of an even and greater than 5. I'll use the greater than symbol. All right, so because it's and, here's basically what you're doing. Once you know how to solve this, you don't have to keep writing this out, but you are first finding the probability of an even, and then you're multiplying that by the probability of getting a number greater than 5. So the probability of spinning an even number is there are 4 out of 8 evens times a number greater than 5. So greater than 5, there are 3 of them, 6, 7, and 8. So that's 3 out of 8. And now you just multiply straight across and reduce your fraction. So that's 12 out of 64, which reduces to 3 out of 16. So that would be your probability of getting an even and a number greater than 5 on the second spin. Letter C, what is the probability? Now this is where you're going to see, well, actually you don't see the word or, but you have to know either order. The phrase in either order means one or the other. So this is where the word or is going to come into play. What is the probability that you will spin a prime number and then a perfect square, but in either order? So what this means, it means what's the probability of doing a prime and then a perfect square, or you could get a perfect square first and then a prime. So you're actually going to be multiplying and adding all in this question, because here's where you're multiplying, here's the ands, and then here's where you're adding, here's the or. So you have to first find this probability, these two, and multiply them together, then find this probability, these two, multiply them together, and then add those two fractions together. So the probability of spinning a prime is 4 out of 8. There are 4 prime numbers up there out of 8. Times, now we want a perfect square. There are only 2 perfect squares up there. So that is 2 out of 8. Wait a minute. There not 2 perfect squares? 2 out of 8. Yes, 1. Oh my gosh. 1 is a perfect square. And 4. 2 out of 8. Plus, now we're going to find, we actually already know these because they're independent, because the first spin does not affect the second spin. So the probabilities aren't going to change at all. Perfect square is 2 out of 8 times a prime is 4 out of 8. So remember, follow PEMDAS, do the multiplication first. So on this side, 4 times 2 is 8 out of 64 plus 8 out of 64. Good news, they both have the same denominators. We can just add straight across on the tops. Denominators stay the same. 16 out of 64, which reduces to 1/4. So you have a 25% chance, or a 0.25 probability, of spinning a prime number and then a perfect square, or a perfect square and then a prime number. So that is if they are independent, which is kind of nice, because the probabilities will be the same for your ors, because the first event does not affect the second event. So your denominator should be common already when you go to add them together. Now, if they are dependent, you need to remember this down here, these 2 asterisks here. When you are given a chart, just report the intersection. Okay, so if you're given a chart, you should be using the chart. Don't try to do like some fancy stuff with multiplying and adding. Just use the chart to get the probabilities, and then if it's or, we add, if it's and, we multiply. So this question is kind of confusing at first, but once we break it down, hopefully you see it's not too bad. So a company was determining the effectiveness of its warranty sales on computers. They took data on the number of people who purchased the 2 types. So you have type 1 and type 2. I don't know what they are, but it doesn't matter. And then if they purchased the warranty after they purchased one of these 2 types. So they want to know if a customer is chosen at random, what is the probability that they did not purchase a warranty? So what we are trying to find is the probability that they bought type 1 and no warranty, or, because they could have bought type 2, we just want to know that they didn't buy a warranty, or they could have bought type 2 and, I wrote type with a 2, type 2 and no warranty. So if you look at this chart, they don't tell us the percents. And remember, we don't ever really use percents in our algebra, we should use the decimal equivalent. So this 68% is 0.68, 32% is 0.32, 35% is 0.35, and 56% is 0.56. Now they want to talk about not purchasing a warranty. Well, these are the numbers for who did purchase a warranty. So no warranty, I'm going to add a column over here because I actually need those numbers. So if 0.35 actually did purchase a warranty, that means 0.65 did not. And then for type 2, if 0.56 did purchase a warranty, that means 0.44 or 44% did not. So now I can find those probabilities. So first I'm going to find the probability of type 1 and no warranty. Or we're going to find the probability of type 2 and no warranty. So ands means multiply, or means add, and we're going to write those numbers down and just do some algebra. So the probability of purchasing a 1 and then no warranty would be 0.68. That's how many, well, that's the percentage as a decimal that did purchase type 1, and means multiply, times no warranty was 0.65, plus type 2, the number of people or the percentage is 0.32 who did purchase type 2. Whoops, I put 2 parentheses there. And then no warranty would be 0.44. Now you're going to multiply those numbers out and then add them together. So it turns out to be 0.442 plus 0.1408-ish. And when you add those up, you get a final probability of 0.5828. And that's your final answer. So if you turn that back into a percent, it's about 58% of the people did not purchase the warranty, given that they did buy one of those 2 types. So that is it for your ands and your ors. So just make sure you know and is multiply, or is add, and you just use the charts, or you might have to actually count up how many elements there are given the certain event they're talking about. But if there's a chart, please just use the chart. Don't try to like multiply any of these together first. Make sure you just literally look at the chart and write down the numbers that go with each probability.